And again, we'll have to play it by ear to see possibility of having in-class presentations. I hope we do, but we'll have to, again, as I said, play that by ear. So now what I want to do is today on the 22nd is get through logistic regression, log linear analysis, and start on structure equation modeling and path analysis. I'm hoping to get on that. Also, what I'd like to do that's not in the syllabus, spend maybe 20 minutes or so just exposing you to some other multivariate techniques that may or may not be in the books. One, I just want you to know about cluster analysis. I just want you to know about finite mixture modeling. I want you to know about survival analysis. I just want you to know what those animals are, just so you have an idea. And there are chapters on each of these in both of your Grimm and Yarnell book. We left off talking about and introducing the logistic regression. I initially just did the basics on a 2x2 chi-square, because chi-square kind of serves the groundwork for logistic regression. Again, how is logistic regression different from multiple regression? Multiple regression, you had a variable that was measured at what? The outcome. The outcome is measured what? Categorical or quantitative? Quantitative. You got it. So for multiple regression, the outcome was quantitative. For logistic regression, it's qualitative. It's a categorical outcome. It's a categorical outcome. So something very different from what we've had. So let me go ahead and open up one of the files here. File, open, data. I do have a file set up for logistic regression. So you found with the categorical analysis, for instance, a 2x2, the chi-square is what, everybody? The chi-square is a function of, what did we discuss last week? Does everybody remember the formula for the chi-square?
Observed, mass expected, over expected.
Yes. Are we looking at our notes right now?
No, I know that one.
Observed.
I really do. I don't know why.
Observed minus expected over expected, right? So you sum up for each cell. How many you have in each cell minus the expected squared over expected. And you just sum it up. Are there any means or standard deviations or covariances there? Any mean vectors, variance, covariance matrices? Not at all. So it's all based on counts, right? Categorical analyses for nominal data is based on counts. As we said last week, if we did a 2x2 of if you're self-educated and no or yes versus stay or managed out. Remember, managed out is a euphemism for being fired, basically. You found that if you educated yourself, you tended to stay in the company. If you didn't educate, you didn't. In fact, it's funny. You read this stuff a lot, and people who write questions into newspapers in the business section about their insecurity on the job, and they always say the more you can educate yourself, take classes. If you're not great on software, take a Microsoft class. Do all those little things to educate yourself. And I know in some companies that made me much more valuable when I would learn a new skill I could maybe train some workers on. So it's really a valuable skill to keep training yourself. So that's a 2x2, everybody, right? Add, as Ross just so said correctly, the chi-square is a function, right, of the observed, right? So you have 4 people that did not educate themselves and 4 that stayed, minus the expected. And last week you found that the expected count is a function of the percentage or count of the row and column that corresponds to that person in that quadrant. So this is just a simple 2x2 contingency analysis. Why do we use the word contingency? Right? The row and column kind of go together. One's dependent on the other, so to speak. And the chi-square is also sometimes called the goodness of fit test, because you're essentially looking at the relationship of basically status in the company and education. So is everybody pretty clear on the 2x2 chi-square? Again, as I said, one big gap between undergraduate and graduate education is non-parametric stats. Is non-parametric stats. A lot of times people don't know this little option right here called Analyze, non-parametric stats, and all the stuff you got if you have categorical or ordinal data. Because undergraduate, maybe you get exposed to chi-square, but then again, how many of you came out of undergraduate knowing about the Mann-Whitney, Kruskal-Wallis, the Friedman test? And even in graduate, you may not get it, because all of a sudden it gets regression and ANOVA. So there's a whole host of non-parametric stats which don't have the same type of assumptions as multiple regression does, or ANOVA. So we found last week, for this 2 by 2, where the degrees of freedom, what does R minus 1, C minus 1 mean?
Rho minus 1 column.
Exactly. So if I have a 2 by 2, Chad, what's my degrees of freedom? 1. 2 minus 1 times 2 minus 1 is 1. And there's tables, right? There's all types of tables for chi-square for each degrees of freedom. So if you have 1 degree of freedom, I guarantee you your critical value is 3.84. For 2, it's 5.99, etc. Now, as opposed to the z or the t, you will never have a negative chi-square. How come? Yeah, it's a square number. The lowest it'll get would be a 0. And what's interesting is, what I went over last week, if you took the square root of the critical value for 1 degree of freedom, it equals a z, 1.96. It equals a z. So actually the chi-square for the single degree of freedom test is closely related to the z test. Okay, everybody, we have a value of 3.04, a p-value of 0.081. Reject or fail to reject using alpha of 0.05. Reject or fail to reject? Yes, which means there's not a significant relationship between being managed out, right, your hiring status, and if you self-educate. Now remember, look at effect sizes, everybody, because if you have a small sample size, you may not have significance. So, here we see we have the phi coefficient, which is actually pretty good, negative 0.39. It's a function of the square root of chi-square over sample size. So 3.04 divided by 20 is negative 0.39. That's really not a bad sample size, effect size. No hard and fast rule, but 0.1 is small, 0.3 medium, 0.5 large. So there's a nice relationship. We only have 20 people. One other thing, just so you know about it, just so you know with a 2 by 2, and let's see if SPSS, let's see if it spit it out. Yes, it did. For a 2 by 2, how many of you have ever heard of Fisher's exact test? The Fisher's exact, which can actually be two-tailed or one-tailed, is an exact test. It's called exact. And this one is actually appropriate, and you'll see it's used in quite a few medical journals when you have small sample sizes and a 2 by 2. It's actually based in part on the binomial test. So the Fisher's exact test is also one option you'll see, especially in a lot of medical journals, used for the 2 by 2. Soon you're going to see this likelihood ratio, which is kind of similar, the chi-square but not the same, is going to be used in logistic regression. Because soon you're going to see it's a function of taking logarithms of each cell. So there's our 2 by 2 chi-square. I always do a graphic. I always do a clustered bar chart. A clustered bar chart is a great idea to show the relationship between two categorical variables. I always use a clustered bar chart. And they're easy to get. They're easy to get, everybody. Here's, just so you know, here's my stay, manage out, yes, no. You go into graphs, legacy, go into bar, hit this option called clustered. Hit that option called clustered. Maybe I'll put status there, self-education there, then I get the percentages. And there you go. So if you self-educated yourself, you're more likely to stay. If you did not self-educate, you're more likely to what? Yes, exactly. And this perfectly shows the 2 by 2 chi-square. And you can, if you wanted to, everybody, you can also have status on the x-axis. So it depends. And how I make a determination which of the graphics to use, I go into the chi-square status there, self-education there. Get all the good statistics. And the story I probably want to tell, is if you're self-educated, looking within self-educated, we can see that 81% of people stayed. Here, if you did not self-educate, within self-educate, 44%. 44% stayed. So you have to make sure you understand the row percentage versus column percentage to tell the story correctly. 81, and how I can tell is 81 plus 18 is 100, so I can tell by looking at the percentages. So I want my graph to reflect 81 and 44. So here, look, everybody, this does not exactly reflect the 81 and 44. I'll show you how I can make it reflect that perfectly. Go back into graphs, go into the bar, cluster it again, and then reset, and now put status right there, self-educate there. (81%), 40%, 44. So in other words, now I can capture the right percentages. You still see that those who stay, they tend to self-educate. Those who manage out, they tend to what?
Not so.
Yes, exactly.
But that, looking at the cluster for stay, doesn't necessarily represent that 88%, does it? The
Okay.
green bar?
Okay, so look here. Do you see if you stay?
Oh, 81.
If you stay 81%,
Okay,
right?
I thought we were
Right,
talking 88,
right.
but yeah, that makes sense.
Right. So it's just so both of those graphs are fine. They're both not wrong. It's just which one tells a story that reflects the percentages. So what I do with my client is I'll give both of them, and then they can make a decision. But usually one is really clear, because one is kind of an outcome. One is kind of a DV, like higher, fire. So then whatever makes sense to reflect the percentages. Whatever reflects to make reflect the percentages. Now, I do want to show you one thing here that I'm starting to do in my reports, if it makes sense, and I'm having my dissertation students do it. I'm having my dissertation students start to add, go into the chi-square, and under statistics, add a thing called risk. And we're going to discuss today the odds ratio when it gets to logistic regression. I'm having students, if it makes sense, to start reporting what's called a risk, a relative risk. And I'm going to discuss that in a few minutes with exactly what relative risk means. And I'm starting to have, Kaylin's working on her dissertation now, and she has this type of risk estimate that makes perfect sense for her study. If it's a 2x2 of sex and ethnicity, that makes no sense to have a risk. But soon you're going to see what risk means is if my DV is that you got fired within a year, and I want to look at sex and firing, I could maybe see for those that get fired, the male-female ratio. The odds is slightly different, and I'm going to go over that, but I do want us to start paying attention to this thing called risk. You do get different effect sizes, everybody. You do get different effect sizes, and usually, let me show you one thing really quick here. Just to show you what you can get with a 2x2. Let me just get all the statistics. Not many people use this statistic. I've been using it a bit. You see this thing called nominal by nominal? And now look, status could be dependent or self-education. With chi-square, usually you don't have a dependent variable. You're just looking at the relationship of two categoricals. But what if one is kind of dependent? There is this thing called the Goodman-Kruskal test, and another called the uncertainty coefficient. And here you can actually have a categorical variable be an outcome, which is what we're going to do in logistic regression. The one that I have used, I do use the Goodman, Kruskal, Dow, and sometimes the lambda. Both of these, do you see where it says nominal binomial? So these are not frequently used statistics when you have a 2 by 2 and you actually have a dependent variable, if you have a dependent variable. So I just want you to know about that. There's a thing called Solmer's D. If you have an ordinal outcome, an ordinal, if you want to look at the relationship of two ordinal variables, similar to Spearman's rho, and one of them is an outcome. So that is an option called Solmer's D, just so you're aware of it. These are directional measures. These are actually called asymmetric measures. They're actually called asymmetric measures of association because one is an outcome. The symmetric measures are the correlations. And you get all types of correlations, everybody. For categorical data, the phi is for the 2 by 2, as you already know. Then you got Kramer's V and contingency coefficient. Those can be used if you have larger than 2 by 2s. If you have a 4 by 4, you will get slightly different values. I do tend to use Kramer's V or sometimes the contingency coefficient when you have larger than a 3 by 3. So everybody, you have a lot of statistics to report for chi-square analysis, and you should always report some type of effect size. You got to report some type of effect size. Okay? You okay there? You yawn a lot.
I do yawn a lot.
You do yawn a lot, yeah.
Indicative of an underdeveloped frontal lobe.
Well, that I'm not a neurologist, so I can't comment on that yet. Some people it's just they just bored.
No, it's
I know.
see that.
But now look.
That could be it too.
So here's a chi-square, but I know this is kind of hard to see. But here you have 7 ethnic groups. 7 ethnic groups, and I'm doing it by education. Now, some high school all the way up to graduate school. This is called a 1, 2, 3. This is a 7 by 5. It's a little busy. And guess what you're going to tend to get? Unless you have a huge sample size, guess what you're going to tend to get? Really sparsely populated cells. In fact, look, other and college graduate, 0. I got some zeros here. Asian American and some high school. So the problem is be mindful when you do categorical analysis. Let's say for your dissertation, your committee wants you to do look at the relation between their department they work in, HR, finance, marketing, and maybe some type of categorical outcome that's at 5 or 6 levels. You're going to have sparseness of cells. And this is a problem, not only for chi-square, but logistic regression. Sometimes you get screwy results, and one thing that a lot of statisticians will say is, do you have sparseness of cells? In other words, what if you have, let's just make it just a 4 by 4. You have HR, finance, cleric, HR, finance, marketing, and manufacturing. 4 departments. And you want to look at maybe Asian Americans, African Americans, Caucasian, Latino. Let's say you want to look at the relation of ethnicity and their department. Right? Let's say you have, for instance, African Americans, no African Americans in HR. So you're going to start to get some problems with these types of categorical analysis when you have a lot of categories. Now, one option you can do is what, everybody? If you have a lot of categories and you have the sparseness of cells, what is one option you can do? What is one option you can do to mitigate the negative influence of cell sparseness?
Combined groups.
Mm-hmm. If it makes logical or illogical sense.
Logical.
Yes, right. Absolutely. So, what you could do is Caucasian versus everyone else. Right? A lot of times Caucasians are the biggest group. We see 66, 45% are Caucasians. So you could do that, but you're losing information, aren't you? A lot of times, I see the next highest group is Latinos, 34. I probably would keep that. So I might do, which I have on slides, is Caucasian, Latinos, and others. But I still see 21 Asian Americans. So then you have to start making these decisions about what makes sense. Now technically, this could be an ordinal outcome for education. Some high school, etc., college degree, etc. So you could maybe do an ordinal analysis, such as the Mann-Whitney, or if you have 3 or more groups, the Kruskal-Wallis. But sometimes I've seen grammar school, some high school high school, associate's degree, post-secondary degree, vocational training. Which one is higher than the other? What's higher, an AA or vocational training? Right? I mean, it's hard to know exactly what is higher to make it ordinal. So keep this in mind, everybody. That if you do a chi-square and you have sparseness of cells, the finding may be a little unstable. That being said, we have 20 degrees of freedom. Right? We have 20 degrees of freedom. It's a pretty big model, isn't it? Right? It's a pretty, because if you have a 6 by 5, 5 times 4 is 20. So you have 20 degrees of freedom. 29.03 is my chi-square. My p is 0.087. But look at the likelihood ratio. Here it's significant. So you do get slightly different results. Now, there is one assumption with chi-square. You hope that no more than 20% of the cells have expected counts less than 5. So if I have a 5 by 5, or 4 by 5, if I have a 4 by 5, I have 20 cells, right, everybody? If I have a 4 by 5, and you don't want any more than 20% of your cells. So 20% times 20 equals 4. I hope no more than 4 of my cells, have expected counts less than 5. Expected, not observed, not the actual count, but the expected. So SPSS will actually spit this out for you. SPSS, 21 cells, 70% have expected count less than 5. And we already knew that there's going to be a lot of small expected counts. It just means that the results can be somewhat unstable. So now, everybody, that's your basic chi-square, which sets the groundwork for logistic regression. So what if you, A, have a true outcome, a true DV, of which you now know you can use the lambda, and there are a couple of tests in SPSS, where if you have a true DV. But what if you want to add interactions, multiple variables, do a hierarchical approach? What if you want to do almost everything you want to do in regression and have that flexibility? Then you're going to turn to logistic regression. For now, we're going to start off with binary logistic regression. Again, I don't know if you've read the chapter in this book on logistic regression. I hope you have. And it's a nice, user-friendly chapter on logistic regression. Chapter 7 starts on page 217. Really a very well done, nice, user-friendly chapter. Also, you should have your Cohen book, right? Hopefully you haven't sold your wonderful book from 6022. And then he's got a great section on logistic regression. That's a bit more technical than this. So it's basically logistic regression is a type of nonlinear model. Now we're moving into generalized linear models, not general linear models. General linear model is subsumed within generalized linear models. And the way to think about generalized linear models is you have this thing called a link function. So you have kind of y is a function of x. But a lot of times you have this thing called a link function. Sometimes it's something like this. It's like g dot mu, or whatever parameter you're doing. And it links the random component and the fixed component. It links them together, and it may use different types of, for lack of a better word to say, certain types of statistics to link them. If it has something like this, doesn't that kind of look like the mean and the standard deviation of the population? That's called an identity matrix. It's called an identity, which is like regression. It's regression. So that's no different than regression. But what if you have something like this? Sure doesn't look like this, does it? So in other words, you may have what's called a logit link function, or a log. So there's all these types of statistics called generalized linear models that use very different types of statistics to link the fixed and random component. Well, one thing is this. You may recognize this from 6022 that we did go over, but soon you're going to find if you have a binary outcome, things like variances and covariances aren't going to make much sense. Things, do you recall what the residuals were for regression? What were the residuals for regression, everybody? Y minus what? Thank you, predicted. And when you did sum of squares, you remembered to square it, right? So that's what sometimes is called the loss function. This is a big part of regression because it was through the residuals that we found the fit of the line. And regression, the goal with ordinary least squares is to what? Minimize or maximize the residuals. Yes, exactly. We want to find a line that minimizes, right? The line that minimizes those residuals. And that is the loss function that is used for regression modeling. And as you know, you got predicted scores from that, right? You got predicted scores. Right there. This is a little bit different. This is a little bit different in terms of the function we will use for logistic regression. Because soon you're going to see a big part is when we get a probability of a score, it's no longer exactly the same with an intercept and slope, but it kind of is. Does that A plus BX look a little familiar? Thinking of which you may have had this in undergraduate, A was your intercept, B was your slope, and X is the value of the predictor. And what does that E mean, everybody? As we've gone over many times since ANOVA. What's that? No, not into this. Think of mathematical statistics. It's the base of the natural logarithm. Remember the base, 2.718, non-terminating decimal? So this is, you're going to find this type of stuff is a big part in categorical analysis. Do you guys remember the good old? Remember log transforms?
A long time ago.
Long time ago. Okay, so here, this gets at the probability of the outcome. And there's two ways to do it that you're going to soon see. You can have this function, or it can also be 1 over 1 plus e and taking the negative of this. Basically, what you see is that, do you see the slope is in the power function? Does everybody see the slope is there? So in other words, that's what helps make it a true nonlinear model. Remember, do not confuse y equals b0 plus bx plus bx2. Remember doing polynomial models for regression, everybody? Capturing quadratic? This is still a linear model. It's still a linear model because it's linear in the parameters. The parameters being the slopes. It's linear in the parameters. This is nonlinear in the parameters because you're exponentiating the slope. This is getting a little more advanced stuff. You know, but that's why these are truly, and people confuse that. They think that regression, when you have a polynomial, that's a nonlinear model. You're capturing a nonlinear relationship, but it's not a nonlinear model. This is truly nonlinear. This is truly nonlinear. And soon you're going to see we can get a predicted probability based on this. So this is what a logistic function looks like. It's got that type of S-curve. It's got that type of S-curve right there. In fact, this is going to come into play. I'm going to be speaking on IRT, item response theory, in a couple weeks in the psychometric class. And soon you're going to see it's exactly this S-curve, the logistic or O-guide function, that serves in equating someone's ability level, say on math, and the probability of getting an item correct. And that 0.5 you soon see will be associated with an intercept for these type of logistic models. This function, the logistic, serves a big part also in item response theory. So here you see that S-curve? It's kind of like a cumulative normal distribution. What do I mean by cumulative? You have a probability of getting it completely wrong all the way to probability of getting it correct. And you get that type of S-curve, logistic curve. And that perfectly fits the logistic function, And your book has a couple of pictures of it. So think of height in inches, regression of sex on height, and maybe the outcome is male or female. It's kind of an odd DV to have male or female, but this is an example I just downloaded from the web. Soon this is the probability of 0.5, probability of being male, female. But let's change this. Instead of being height, it could be maybe some type of intelligence measure and the probability of getting an item correct. Do you see along all aspects of the domain, the DV, you can go ahead and see what's the probability of getting an item correct, the probability of the outcome given their score. And that S-curve captures it really nicely. So it's kind of like a cumulative distribution function. And here's the probability. 0.5, get it right or wrong, and where it crosses the axes, you will be able to see, given their ability level, given their value on the predictor, what's the probability of getting the item correct. So this S-curve conforms to this beautifully. And soon you will see that B will be the log of the odds, called a logit, which is going to be your regression coefficient. So let's start off to make sure you understand what an odds is. You have a research question where you have a dichotomous outcome. What does dichotomous mean? Two options. Live or die. Fire, not fire. Pass, don't pass. In organizational psychology, promoted, not promoted. There's your dichotomous DV. Now, a big statistic of logistic regression is called the odds or odds ratio, which we did go over in 602.2. The odds is just the ratio of probability of event happening over probability of it not happening. That's the odds. People a lot of times confuse odds and probabilities. An odds is a ratio of probabilities. So for instance, the odds of getting an ace. How many aces in a pack of 52 cards? 4. So 4 divided by 52, right? 4 divided by 52 is 0.0769. So then the denominator would be what?
923.
Which is the probability of?
Not getting this.
That's exactly what it is. So essentially, when you think about it, everybody, this is what the odds looks like. 4 divided by 52, 48 divided by 52. So don't confuse this. This is the odds, right? That's the odds, which is really a ratio of ratios. So odds is the probability of an event happening of it not. The probability of having an ace is 0.0769. The odds of getting an ace is 0.0833. The odds of getting an ace is 0.0833. So it means that there's kind of a lower probability. The odds of getting an ace are fairly low. This is not a percentage, everybody. That's not a percentage. Because a percentage can go from what, everybody? 0 to what? 1.0. And odds can go from 0 to infinity. There's no upper bound. There's no upper bound for an odds. Now, this is kind of a little thing that I want to go into about why we do logarithms of so much of this math. Why don't we just keep it as a count and make our life easier? Odds can be found by counting the number of people in each group and dividing one number by the other. However, in our odds, for instance, what if we have the odds are 0.9 over 0.1? Let's say 90% of people get A's in my class. Let's say 9 out of 10. 9 out of 10 people get an A in my class. Right? Which,
That's not true.
it's not unlike, I know, but let's go with it. Go with it, Chad. So 90% over 10%, right? 9 to 1 odds. 9 to 1 of getting an A in my class. Or being male, whatever the outcome is. So it's almost like you could say there's almost a, if you convert it to a percentage, 900% over, right, of getting an A. Now, what about the odds of being female, because that was for male, or not getting an A? Not getting an A. 0.1 divided by 0.9. Do you see I just switched the ratios? Is 0.11. Well, that's not very symmetrical. Right? You have a 9 to 1 odds of getting an A, a 0.11, a lower odds of not getting an A. So how do we make it symmetrical? By the natural logarithm. By the natural logarithm. So you guys all have your calculators out, assumedly. And hopefully it's got a logarithm function. Hopefully. So you have just a little generic calculator and it's going to do the trick. You should have an LN button. Do you see an LN? Not an LOG. You should have an LN, and above it, you should have this above it. Usually your calculator will have this above it.
Yeah.
E to the x power. So go ahead and take ln of 9. Take the natural, remember not the log button, that's the common logarithm. Take ln of 9 and tell me what you get.
2.197.
Good, 2.2. 2.2, you took the log of that, and it's basically the log of 0.9 over 0.1. Please take the log, please also take the log of 0.11 and tell me what you get.
Negative 0.22.
Negative 2.2. So guess what? The natural log retains the symmetry. See, it takes the natural log of 9 is 2.2, the natural log of 1 divided by 9 is negative 2.2. So what's kind of cool is why they use the logarithm for all this is when you have odds, it retains a symmetry. So if 90% of people are going to get fired, the log of people getting fired will be just the reverse of the log of what? Not getting fired. So the odds will be very different. So that's what's kind of nice, everybody. Here's a natural log function. Here's the natural log function. Here's the odds of something happening and the log. Taking the logarithm of the variable. Try taking the log of 0. Take ln of 0 and tell me what you get.
Error.
Yeah, that becomes a little problem when you do a transform. If you have a non-normality in SPSS, you ain't going to be able to take the log of that value. If you have number of times they've been absent in the past year and you want to transform it, you can't take a log of 0 if someone's had 0 absences. So you need to add a constant, usually like 0.5. Usually if you add a constant, you'll be able to take the log of it. So here, everybody, you can kind of see what's the exponential function. That's why how many people have ever heard terms, there's an exponential growth in language development of kids. When you go from 2 to 5 years old, right? You have a young one, you see from 2 to 3 to 4. Is your vocabulary expanding as quickly as your kids per year?
No.
So absolutely, so you see that type of exponential. Guess what has the negative exponential function? The forgetting curve. Supposedly you lose 80% of what you learn within a year. Do you buy that? Do you buy you forget 80%? You say yes, why?
Maybe like 80% of the new information in the year.
Okay. Okay, why?
Because it helps you consolidate memory.
Consolidate your
Things that you
brain.
need to remember.
Okay.
Somebody was studying for bioaspects.
What's that? What's that?
I was up all night studying for bioaspects.
Oh, okay, right. And when you cram for a test, that's
All that.
very different than really trying to understand, right?
Totally.
Very, very different levels of trying to just get that information in so you can spit it out versus really, really, truly understanding it and incorporating it.
Isn't there an aspect of, like, you may not remember it from recall, but you learn it easier if you learned it before? Is that part of it too?
Probably so. I mean, I'm not a cognitive psychologist, but
Yeah, I
probably.
mean, it's off subject, but just,
Right, probably. So this is an odds ratio, everybody. Soon you're going to learn that the log of the odds. Soon you're going to learn the log of the odds is your regression coefficient, called the logent. So linear, and we're going to go over that soon, everybody. The log of the odds will be your regression coefficient. So linear regression is a least squares method, as I said a few minutes ago, right? We're minimizing the squares to optimize the fit of the model. Logistic regression uses maximum likelihood. We've gone over maximum likelihood a few times. You may have even played around with it in EFA. Maximum likelihood says there's certain parameter estimates that will maximize the probability of the observed data. And again, one way I showed you this already, one way that made it really clear what maximum likelihood is doing. If there's a target right there, and I do this, how close am I?
Not very. Better getting closer. Not sure. No. Yeah, there you go.
Right. So in other words, you may be, if we think that there's a universe of means, right? A universe of means. Let's say the average person is 70 inches. Maybe I start off with 50 inches and go to 90 inches. Let's say 70 inches is the true parameter estimate, which we really never know unless you've had the luxury of measuring everybody. But I can get a probability, right? Thinking of h, remember h, which is the ordinate of the curve. And you can get a probability density function associated with every single inch here. I can go ahead and find which parameter estimates maximize the likelihood of the observed data. What maximizes the likelihood of the observed data? How do you feel about 48 inches? Very good. How do you feel about 93 inches? Very good. What about 74? Is that a little better? Exactly. So then what you end up doing, everybody, has anyone ever seen uppercase V? What that means? It sums the products. It sums the products. So if you have something like this, everybody, if you have 3, if I do 1 to 3, 1 times 2 times 3. So this is the sum of the products. So it does all these probabilities, a lot of these probabilities across the entire probability, across the entire function, which means computers would be very nice. Because part of the mathematics of logistic regression, structure equation modeling, multi-level modeling, uses maximum likelihood, and part of maximum likelihood is solving for these things called second partial derivatives. How many of you had calculus? You did? What's your recall of the second partial derivative?
I dropped out of calculus.
Okay, so that means that, so essentially the second partial derivative kind of gets, it's kind of like a partial correlation. It's y controlling for an x. It's kind of like y over x controlling for all these other variables, and it solves for 0. It solves for 0, which means you get this matrix of second partial derivatives, and you want computers to do it. That's why a lot of this stuff was much easier to do once you had computers from the 70s on, doing maximum likelihood. The problem is you'll find in structure equation modeling, sometimes you get stuck there. And we'll discuss this. Sometimes you get stuck here, what's called local. There's local maximums and global maximums. So sometimes these models, when they don't converge, which is the error message you got in EFA, when they don't converge, they go through 25 iterations, 30, because maximum likelihood starts with estimates and puts it back in the model. Recirculates them again, puts it back in the model. Recirculates them again until we get this, until we solve for 0. Well, sometimes things don't work out so well. And that could be due to very small sample sizes, cell sparseness, multiclinearity, all those things. So now let's run our binary logistic regression, take the same variables, but cast one as an outcome variable. So let's have status, managed out, versus stay as the outcome, and self-educate as the binary predictor. Okay, so here, which all you have to do for binary logistic regression, everybody, you'll be doing this for your take-home, is you'll do analyze, regression, and then you'll go to binary logistic. Your dependent variable will be status there, self-educated will go there. Just so you know, it may be confusing to see the term covariance, but you're going to see sometimes that's an umbrella term for explanatory variables. Sometimes covariance will be really a covariant, but sometimes it's just an explanatory variable. It's always a good idea for categorical variables to also put it under categorical covariant because it'll dummy code it for you. In other words, what's really cool about logistic regression, you don't have to create dummy codes. If you have 3 or more categories, it does it for you. It does it for you, everybody. And then under options, classification plots, goodness of fit test, and confidence intervals. I always like to get a lot of this stuff. And now you're ready to run your binary logistic regression. Code your outcome as 0 and 1. Code the event you're most interested with a 1. It'll make life easy. Because do you see this thing called dependent variable encoding? Otherwise, SPSS will do it for you. And I never like the computer dictating the values of my outcome. So in other words, if you have a 2 and a 3, it'll recode it to a 0 and 1, and it may even do it based on alphabetical, alphabet. So here, managed out is my main event. If you're being booted from the corporation, that's the one I want to go ahead and have a 1. So I always like to manipulate and control the coding. Also, have your predictors be 0 and 1. If you have a binary predictor, it'll make it much easier to interpret the coefficients. Because look what SPSS is going to do anyway. It's going to dummy code it for you anyway. Just so you know, the default may be something like this. Here, those who do not self-educate get the 1. But you can also have the yeses be the 1. Just like multiple regression. And here's what you do, everybody. When you go to Analyze, Regression, Binary, when you go under, again, put status there, self-educate there, and under Categorical, put self-educate, and look, Indicator, you can just change it to the first. So here you can change first or last, depending if you want the first, if you want males to be the main coded one, the reference group, so to speak, or females. So it's like coding for your reference group, so to speak. So, the output can be a little overwhelming if you've never ran categorical analysis. There's some parallels to regression, some that's very, very, very different. So, what it starts off with is what's called block 0, which basically is the first block of entry and has no predictors. Sometimes it's called the intercept or origin only model. Basically, there's no predictors in the model. So it's basically like, it'll be almost as if in multiple regression, if this was your only predictor, your intercept. No predictors. So that's your starting model. That's your starting model. Or what some people would call essentially the most restricted model, because you don't got nothing in there. So the first step, it uses maximum likelihood. It goes through iterations, just like factor analysis. All these advanced statistics go through iterations. They start with initial estimates, then through maximum likelihood. Maximum likelihood tries to hopefully improve. So your maximum likelihood hopefully goes down. This is called -2 of the log likelihood. So why? Because we take the logarithm of the likelihood, the log of the like, and then multiply by -2. And one reason I used to ask, why do we do -2 log likelihood? And they say it makes the math more tractable, which didn't answer my question. But I remember reading that years ago. It makes the math more tractable. And then I found one book that made it so easy to understand. See, if I have 50 to 90 inches, and let's pretend the probability density function can do it in 1/8 of an inch. Lots of numbers here, huh? Lots of probabilities. And guess what happens? Guess what happens when you start trying to multiply a bunch of low probabilities? It exceeds actually the memory capacity of the computer. In other words, when you try to take the product and sum them up of all these low probabilities, sometimes you won't even be able to get a solution. So taking the -2 log makes it easier to calculate, makes it much easier. So that's actually the answer. Thinking about a likelihood, remember we discussed this briefly in discriminant analysis with Bayesian Bayesian theory. Bayesian theory was the likelihood times the prior, and the likelihood was the probability of the data given your hypotheses, and that's a likelihood. So here you get these log of the likelihoods. A perfect model is a 0. A perfect model would be 0. You want the numbers to get lower. So here is the intercept-only model, no predictors. Soon you're going to learn you get what's called a classification table, which, similar to discriminant analysis, is very, very, very helpful to get at what? False positives, false negatives, true positives, true negatives. However, we have a vernacular that you see in logistic regression, but not discriminant analysis. What's called sensitivity and specificity. Soon you're going to see sensitivity is your true positives, specificity is your true negatives. Soon you're going to see this line is sensitivity, this will be specificity. In your origin-only model, you hope to improve upon this. No predictors. So here we see, everybody, for managed out. Do you see we did not classify anybody correctly? Look at 0%. 0 out of 7 are managed out, were appropriately predicted to be managed out. So that's pretty bad, isn't it? Specificity, we were perfect. 13 out of 13, those that stayed, were perfectly classified. So overall, we did 65% overall, because 13 out of 20 people are correctly classified. But why am I not happy with that? We didn't do a good job for any managed out. So that's my no predictor model, and of course I hope to improve upon this. So here's the variables in the equation for the intercept-only model. Now generally you will not report. You can if you want, but generally this is not reported in statistical output. But I just want you to know where the model starts. So here you get something that looks a little similar to linear regression. Do you see that B? Kind of looks like a coefficient, doesn't it? But this is called the logit. This is the logit, the log of the odds. The log of the odds. So you see that 0.538? Please take the logarithm of it. Please take the log of 0.538 using the ln button, not the log. What do you get?
Negative 0.62.
Mm-hmm. Negative 0.62. Go and exponentiate it. Use your EX button, everybody. You should have an EX button. Hopefully, you should have that above your LN button. If you take EX and plug in negative 0.619, what do you get?
Negative 0.479.
No.
1.86.
What's that?
1.86.
No. If you did negative 0.619.
0.538.
Yes, 0.538. There you go. You mean there's a chance you forgot the negative sign there, Stacy?
I did.
Did you get 0.538 just now? So if you took E as the base and then have negative 0.619 as the power, you'll get 0.538. So everybody, what does that mean? That's the odds that you're going to be managed out. That's the odds that you're going to be managed out. And how do I know that's true? Do you see 7 out of 20 people were managed out? 35%? Do we see that 13 out of 20 people were stayed? Would you please be kind enough to take 35 divided by 65? Tell me what you get. Just take 35 divided by 65. Do you get about 53.8? Do you see how easy it is for that? So there's your starting model, everybody, in logistic regression. It's basically, here's the odds of managed out. That's it, everybody. So that's the starting point. That's the starting point. And I can also get a predicted probability that you're going to be managed out from this first one. If I took that little formula, this little formula right here, e to the x. If I took this little formula, and you already told me that it is, there's a couple ways of getting at this, of 0.538, but please tell me what 0.538 divided by 1 plus 0.538 is. Please, 0.538 divided by 0.538 divided by 1 plus 0.538 is what?
0.349.
You got it. Look, 35%. There you go. So guess what? From this formula, and it can also be a negative, E negative 0.619 plus 1 plus minus that is 0.53. That means there's a 35% probability you're going to be managed out. So what's cool with logistic regression, I not only get the odds that you're going to be managed out, I can use that by a very well-known formula right there, e to the x power over 1 plus e to the x, the probability of being managed out. So there's a 35% chance you're going to be zonked from the resource restructured, career exploration opportunities, fired, hired, downsized. And that's it, everybody, for the first step only. First step only. So do you kind of get an idea of how this is working? Have fun interpreting that. I haven't even addressed how to interpret it. We know with linear regression, if you have a 3.0 for job satisfaction predicting performance, and 3 is your regression coefficient, it means as I go from 1 to 2, 2 to 3, there's a 3-point increase in performance, right? this is not fun to interpret. This would mean as I go from a certain variable, there's a negative 0.619 log odds change in the outcome. And guys, it's not easy to interpret a log odds, right? I mean, that's a really different type of metric. So now we're ready for the main part of the model, to add our predictor. Now we're ready to add our predictor, which will be if you self-educate. So does everybody see that's the origin-only intercept model, of which a lot of it you were able to recover from your frequency table. So now you got the log likelihood, but now we've added self-education. And the log likelihood goes down to 22.78. From the first model is 25.89. Please subtract those. Would you be kind enough to take 25.898 minus 22.796? What do you get?
3.10.
3.10. There's your chi-square test. So there's the chi-square test of model coefficients. This tells me now that I add one predictor, hence 1 degree of freedom, my model P is 0.078. Reject or fail to reject? Yeah, which means guess what? The predictor really didn't add to the model. But it sure was better than the other one, which was like a 0.81. But here, it just shows you how much does my model improve, so to speak, because it's a difference in the -2 log likelihoods. It takes the fit of the most restricted model, which has no predictors, then a less restricted model with a predictor. So it subtracts the log likelihoods of two models. It basically takes -2 log likelihood of the null model, -2 likelihood of our full model, indicating added education did not significantly improve model fit. So would we be happy or sad if this was true data? Would we be happy or sad with these results if it was true data? Yeah, we would not be very happy. Ultimately, you would love to have significance for this. You would love to have significance. And what I want to show you is the parallels. Do you see the p-value of 0.078? 3.101? Look from the chi-square. 3.101, 0.078. So remember I told you the likelihood ratio will be equivalent to logistic regression. And basically, what is a likelihood ratio? It essentially sums over for each individual, if they got a 0 or 1, where they managed out or not, logarithm of their predicted probability plus 1 minus their score, logarithm 1 minus predicted. So basically you have a predicted probability for each individual, and you just summate over each individual. For 10 people, you can easily do it by hand. Beyond that, you want computers to do it. But basically, this is the likelihood ratio. Another way of looking at the likelihood ratio chi-square test, it's a function. You have double summation over all individuals, and it takes essentially 2 times the frequencies. So if I have 8 people that were managed out, and you take the logarithm of those 8 people over the expected over all cells. That's called G square, the likelihood ratio test. So there's all these things that are kind of similar to chi-square. And look, they have an R minus 1, C minus 1 degrees of freedom. So you're going to see a lot of parallels there with the likelihood ratio test and chi-square. You do get effect sizes that you got to be really cautious about interpreting. You do get what's called, from the SPSS, there's quite a few others, called the Cox-and-Snell R-square and the Naglecki R-square. They're a thorny issue, and in Maynard's book. Maynard has a wonderful book on logistic regression. If my students in their dissertation are going to do logistic regression, I strongly urge them all to buy Maynard's book. Excellent, user-friendly book. Because first of all, they don't top out at 1.0. Could you get R-square of 1.0 in regression? You can't, because it's actually a function of ratio, log likelihoods. So just for fun, everybody, just as a quick little review. Remember you calculated the subtraction of the likelihoods, and you got 3.101. Remember how you got that, Chad? Please take that 3.101 and divide it. And divide it by that initial one, which was 25.898. So tell me 3.101 divided by 25.898. Tell me what you get approximately.
It's about 0.12.
Yeah, I mean, just rounding error. You're really close to 0.14. It's a function of likelihoods. And they don't tap out at 1.0. There are problems with them. But these are, that's why they're called pseudo R-squares. A lot of times these are called pseudo R-squares. And you could report those in your dissertation, but be careful about things like 19% of variance, because it's a very different mathematics. And I do talk about them and give you some information on different effect sizes from the UCLA website. Just so you know, everybody, UCLA has a fantastic website, a statistic website that has examples in SPSS and Stata and R for all these statistics. Really, really useful. Very useful. So it shows you the different types of effect sizes, and they're all a function of the log likelihoods. Okay? So everybody, soon you're going to see what this means, the Hosmer and Lemeshow test. They actually have the initial classic book on logistic regression. Soon you're going to see when you have degrees of freedom. We only have a binary predictor, so there's no degrees of freedom. You're going to be able to see this as a goodness of fit test, and you don't want it to be significant. Once you started adding predictors, you hope that the data fits the model, which is non-significant. So I wanted to show you an example of adding another model, and I have a P of 0.987 for the Hosmer. If you have non-significance, you're happy, because that means the model fits the data. Now this chart I don't look at much, but I have a buddy who's a statistician for Kaiser. You do get this contingency table that breaks things up into deciles based on the predicted score. So if you have a lot of predictors, you'll usually get 9 of these deciles. And you can kind of see that the observed and expected are out of whack for any specific decile, from the 10th percent to the 100th percent of the predicted scores. And see sometimes where things go awry. Okay, let's see if we improved on sensitivity and specificity. We did do a little bit better, kind of. Sensitivity is 71%. Do you remember it was 0% without the predictor? So now 5 out of 7 people were correctly classified as managed out. So that's the true positives, everybody. This line right here is the true positives, and here's the true negatives. 9 out of 13 have been correctly classified as staying in the company, 69%. So the overall hit rate is 70%. Not bad, not great, not bad. So here, everybody, you have the true positives, which is sensitivity, and this is specificity. Then you also get positive predicted value, negative predicted value. Positive predicted value, 5 out of 9 people were correctly predicted. 5. Does everybody see the 5 divided by 9? And this is called negative predicted value, which means 9 out of 11, 81%, were correctly predicted. So, positive predicted value, negative predicted value. Sensitivity, specificity. In medicine and in psychology, a lot of people are more and more important in sensitivity and specificity. This statistic has been used in biostats for years and years and years, and now more so in the psychological sciences. It kind of looks like discriminant function analysis, doesn't it? Doesn't it look a little bit like it? But what are the differences? You don't have assumptions such as multivariate normality or homogeneity of variance covariance matrices. You don't have those assumptions for logistic. Logistic is much more flexible. I can have categorical predictors, interactions. I don't have these assumptions. But you will, for your take-home, compare both techniques and see if they come up similarly. And here's the summary of your coefficient, or coefficients. Here we only added a binary predictor. And you have to remember how self-educated is coded, everybody, the binary predictor. So you interpret it correctly. Here's your full equation. negative 1.504 plus 1.727 times self-education. And this is the intercept. Then you get the standard error. Does everybody see the standard error? Standard errors are interesting in probability. Because just for a binary variable, the probability of event, right, P times Q. P is, this is 80%, this is 20%. Divided by sample size. Square root. That's the simplest example of a standard error for a binary variable. So, if I have 80% of people passed the test, 20% did not, and I have 100 people, there's your standard error for a binary variable. See, this is the variance. 0.8 times 0.2 is 0.16. That's the variance of a binary variable. So here, how do I interpret this? Negative 1.504 plus 1.727. It is not a significant predictor, 0.084. And there's the odds, 5.625 for that predictor. It's the odds. So if I took 1.727 and exponentiated, it means there's a pretty high odds, 5.625 odds, right, that you will be managed out if you don't self-educate. You have to remember how you code your predictor, just like the point by zero correlation. So the higher odds is associated with being managed out if you choose not to self-educate. And there's the confidence interval around the odds, which can be really wide because it's very sensitive to the unstandardized coefficient. It's very sensitive to the numbers, the probabilities, and it can be really, really wide. And it's also, which means the standard error is impacted. Things like sample size. I do want you to know, everybody, and I gotta admit, I've made the same assumption. You will see power analysis programs that use the odds or odds ratio as a type of effect size. You will see that in power analysis. If you ever have a logistic regression and you need to do a power, the odds sometimes will be the effect size. Scott Menard in his book says it's not a type of effect size. It's not, because he said, look, what is this a function of? The unstandardized coefficient. If I exponentiate 1.73, guess what? It equals 5.6, which means it's a product of the unstandardized coefficient. Now again, if this confuses you, you can just change the coding. Right? You could just change the coding of the group. And now you get negative 1.727, 0.223 is the intercept, and the odds now is 0.178. What does that mean? That means, again, the way to think about it means there's a lower probability of being managed out if you're not self-educated. Right? Which means there's a lower probability of being managed out if not. Now those are two double negatives. So what'll help is make sure you got the coding correct if you have a binary predictor so people aren't confused. I've seen people make mistakes on male and female. They forget how they code it. Females will have a higher probability of having myocardial infarction. And I'll look at the data, I'll go, no, males do. You're not interpreting the coding correctly. And that's that's a huge decision you're making. So just make sure you're really clear on the code. So notice the width of the confidence interval is very much impacted by the metric, or the coding. So the odds ratio for the first example is 5.625. Confidence interval goes from 7 to 42. Here, the other option is the odds ratio is 0.178. They have the same p-values, but confidence interval is 0.02 to 1.3. So what you're going to get, everybody, you're going to get slightly different confidence intervals contingent on the coding. And the Wald statistic, everybody, is your test of significance. The Wald statistic is the ratio of this over the standard error squaring that ratio. Kind of like a regression. The t was the parameter estimate over the standard error. This over this, squared. And that's what gives you your Wald test statistic for a logistic model. That's your test statistic. And we see, again, that we do not have significance. As you know, we can convert these to predicted y's. So here's my regression solution, 0.223 plus negative 1.727, and let's put in a 1. And the predicted score is negative 1.504. That's your predicted score. And if I do e to the negative 1.504, which is the predicted score, this essentially equals 0.22 over 1.22. That means there's an 18% probability of being managed out if you're self-educating yourself. 18%. So do not confuse odds as a probability. Okay, odds of something happening versus a probability. You have to use that little formula right here, e to the x over 1 plus ex, to get at the probability. Now what if you want to know the probability? Probability to be managed out if you're not self-educated. Negative 0.223 plus negative 1.27, put in a 0, because you're not self-educated. Put in the same formula, and there's a 55.6% probability you'll be managed out if you're not self-educated. So that's how you convert. And it's a very useful statistic to probabilities. And this is what my clients want to know a lot. They go, Dale, given a score of 1 on this, 2 on anxiety, 3 on quality of life, what's the predicted probability that they're going to have a heart attack? And that's how you do it by hand, but you can also get the computer to spit it out for you. You go to this option called Save, and look, you can get probabilities and group membership. You can get SPSS to spit out the predicted scores. There you go. Here we see 0 for status, 1 for self-educate, they educate themselves. And look, there's your predicted probability, 18%. So which means if you don't self-educate yourself, you have a higher probability of being managed out. And look, everybody, for people that do self-educate, 56%. So there you go, everybody. There's your predicted probabilities. Predicted probabilities. Now there's a little problem. Did we perfectly classify everybody? Did we have a 100% hit rate for sensitivity and specificity? No, we had 70%. Which means sometimes, as with discriminant function analysis, you misclassify. So here, everybody, here we have someone, right, who's got a 0 on status, right? Keeping in mind what status is. 0, you're staying. 1, you're being managed out. And look what we predicted. PGR means predicted group. Oops, they were predicted 1. Notice, do you see this person was misclassified? See, 0, 0, good. 0, 0, good. Look at all these people right here, misclassified. Oops, these 2 people, misclassified. So here we see that you can get the number of misclassifications, which corresponds to your classification table. So now, everybody, now you know that you can get, as you see, still get the same p-value, 0.094. Regardless of self-educated, how it's coded. But you may interpret the odds differently. This 5.62 means, you know what? There's a higher odds you'll be managed out if you don't self-educate. This lower means there's a lower probability, lower odds of being managed out if you what? Yeah, exactly. They still have the same p-values, they just have very different confidence intervals. You see, same exact wall, same p-value, but different intercepts. Different intercepts, which makes perfect sense. Because how you're looking at this. But what's nice is, do you see it retains the symmetry? Do you see how it retains the symmetry? Because if I take the log, right? If I go, regardless of how you code self-educated, look everybody, 1.727, negative 1.727. Very different odds, but when I go and take the log of both of these, they retain the symmetry. Which means there's kind of a normal distribution. So that, everybody, is kind of the overall summary of virtually everything you get from logistic regression. There are certain things you can look at, like predicted logits, you can look at certain graphics, but that just shows you with one predictor, and we almost got the same results as a 2x2 chi-square. And that is logistic regression. Issues to think about. Rare event data. I was just having lunch with a fellow statistician last week who's got data like this. When you have people that don't have very much of the event. What if out of a company of 3,000, really only 4 get laid off in a year? That's a rare event. Are there some diseases that are very rare? Avian flu, hantavirus, right? A lot of times epidemiologists, they may look at a certain area, geographical area, look at prevalence and incidence of a disease. They may only have a rate of 3 out of 100,000 that have the disease. You still could do logistic regression, but it can be kind of unstable with rare event data. The confidence intervals can be screwy. I've been on a study where less than 1% of children have respiratory distress syndrome. RDS is when the kids lack surfactant in their lungs, and it can be, they can die from it. It's a very scary disease. And I did a research with a perinatology group at Sharp Healthcare on that. So Gary King has done some really cool stuff with logistic regression and rare events data. It's actually in a journal called Political Analysis. Because guess what event is kind of rare, relatively speaking? War. And that was his thing, looking at wars. I mean, there seems like there's a lot of wars, but relatively, when you look at over time in all the countries, there's very few wars. So logistic regression, he actually has. I don't know if he's got it set up for SPSS, but I just saw an article last week that he's got some macro, I think for Stata, which I do use, that can give you the proper probability estimates for rare events. And here, everybody, again, looking at the status, looking at the self-educated, self-educate not, stay, managed out, you get a predicted probability, you get predicted group, and you get a residual. You get a residual. 0 minus the probability. 1 minus the probability. And you get standardized residuals. And then you can take the standardized residual divided by the square root of p times 1 minus p, which is the probability of event happening and it not happening. And you can get a standardized residual, just like regression. You can get residuals and standard deviations and see if something is screwy with your model. So there you kind of get an idea of the mathematics behind the predicted scores and the deviation scores. So there, everybody, is what's called a simple binary logistic model. Why do I say simple? How many predictors did I have? But usually you're going to have much more than that. Which means usually you're going to have multiple logistic regression. Usually you're going to have multiple predictors. Let's say I want to add age as a covariant, a continuous level variable. Now I'm going to add age as a covariant. Guess what? How am I looking now with my overall model? Is this significant? How can I tell I have 2 predictors in the model? Yes. And look, my chi-square went all the way down to 15. Remember, it went down only about 22. So now remember it was like 27, and now it's all the way down to about 15. Which means adding age was a helpful predictor to predicting if you're going to be managed out. And look at my effect sizes. Keep in mind they're pseudo R-squares. They sure went up, didn't they? So now, does it look like so far that it's helping my model by adding age? Absolutely. Here's the Hosmer and Lemschel test. And you hope it's not significant. And we have a p-value of 0.995. Because you don't want significant. And now you see it breaks it down to 9 deciles. And I can see if there's any huge differences observed and expected. I will admit, I don't think I ever use this table, but my colleague at Kaiser uses it a lot. He said, because I like to see at which decile the predicted probabilities where things get a little bit screwy. Here's your classification test. Did we improve? Remember overall hit rate used to be 70%? Now it's 90. Now we've got 85%. 6 out of 7 were managed out. 12 out of 13 stayed. We're really improving, aren't we? Think of that intercept-only model. Think of the 1 predictor model. And now when I add age, the model really improved. And guess what, everybody? Both predictors are significant. Remember, on its own, self-education wasn't significant. Now it is. 0.042, 0.036, age is significant. So now we really see an improvement in model fit by adding the second covariant. How can I tell from the confidence interval that we reject the null for both of those? What would anyone like to guess what the null value is for an odds? 1.0. The null value for an odds is 1.0. Have you ever heard the expression, the odds of a horse winning is even odds? What's the probability that a horse is going to win? Yes. So think about it, everybody. 0.5, the horse is going to win. 0.5, the horse is going to lose. 0.5 divided by 0.5 is 1, or they say 1-to-1 odds. So the probability a horse will win is 50%. The odds is what? So the null value for an odds, is 1.0. So if the confidence interval does not include 1.0, I can see if we have significance. Do either of these include 1.0? 0 to 0.7, 0.57 to 0.98. So I can see we have significance for both of those because they do not include 1.0. So now we have significance, everybody. Quick point, odds versus odds ratio. Odds is probability over 1 minus probability, right? Everybody's got that? The odds ratio would be probability over 1 minus probability, maybe for females. Probability, 1 minus probability for males. So that's an odds ratio. So there's the odds for getting an ace. That's the odds ratio. Maybe takes males over females. And that's an odds ratio. So now, how do we interpret this? Here we see with age, now we got a continuous variable. Things get a little tricky. But you can get a predicted probability by putting in 28 years old, 29 years old, 30. And for each one, we can get a predicted probability based on this full equation. Based on exponentiating 14.49 plus negative 0.285 times 28 years old, plus negative 0.7904 with a 1, meaning that's self-educated. And I get a predicted probability for someone who's 28 years old and self-educates, a predicted probability they'll be managed out. And that comes up a lot. A lot of times physicians are interested in if I have someone who's 70 years old and they've had a heart attack, right? And they have a cholesterol of 332, what's the probability that they're going to have be readmitted? That's why a lot of these algorithms, these risk-adjusted calculators, a lot of times the black box is logistic regression. The black box behind a lot of these is logistic regression. Now again, what if you want to interpret that negative 0.285? Well, it kind of means as I go from 28, 29 years old, 29 to 30, 30 to 31, there's a lower odds, right? The lower odds, the less probability of being managed out. But it's hard to interpret because it's in log odds. It's in the log of the odds. And so what I just want to show you, if I want to add age to my predictor, to my predicted equation, and if I want to go and save probabilities of group membership, so let's say for this person, they've stayed and they've self-educated. Okay, so they're in the company, they're self-educated, and they are, well, that's just a coincidence, 28 years old. I just didn't know my first one was 28. 21% probability. 21% probability they're going to be managed out, given that scenario. Now let's look at this person. They've been managed out, and they're 29 years old. And they do not self-educate. Wow. 99%. They should probably update their resume. Right. First of all, if this was real data and people wanted to make decisions, the first thing I would say, even because both are significant, I'd say, guys, let's cross-validate this in a larger sample. It's 20 people. I feel really uncertain saying that all 29 years old who don't self-educate, boot them out. I would not want to have that type of confidence unless I get a larger sample. But you see how valuable this can be for the user of the data to be able to get these predicted probabilities of an outcome. And let's say that Zach all of a sudden says, well, did I notice that you haven't added like sex, if they're male or female? So Zach maybe wants to know, does it improve the model much if I add sex? the overall significant. Hit rate is the same, 90%, and sex has a p-value of 0.568. So sex did not. And I do that a lot of times with models. We'll add new variables, see if it improves. So that, everybody is binary logistic regression. Let's take 15, and we will move on to multinomial logistic regression and then log linear analysis. Go ahead and take 15 minutes. It's 10:31. We'll see you at 10.